All right, Euler's method. Now, usually when I teach things on my site, I'm always trying to not do the proofs. I'm not going to really explain the math behind things. I just want to help you get through the problems as quick as possible and learn how to do them. And that usually involves plug and chug and sort of like just go into the problems immediately. This is an unusual case where teachers, when they teach it, they don't really explain that much about it. They go straight to these really abstract, weird math problems, crazy formulas like this one, and it just doesn't make any sense and becomes this plug and chug fiasco. And because these problems are so long, if you do it wrong, it's extremely frustrating. And I feel like students really hate this topic because it makes no sense and they are so long. So real quick, I want to explain what are these things, why are we doing this, and kind of where does this formula come from? Because it actually is a little bit interesting once you get into it. And then it'll help you understand like why you're doing what you're doing, and also help you spot the problems other than the word approximate. If you ever see the word approximate the function in your calculus class, you're probably looking at this. If you're in differential equations, you're on your own, but really this is for those, some students have to do this in calculus class as part of the differential equations chapter, which sometimes includes a numerical methods section. So that's why you may be seeing this. All right, so what's going on? I mean, what is a slope field? Why did we do that? Well, there's these situations that arrive in like real life where they use differential equations a lot, which I've heard is in things like anytime they're like doing crash testing, like simulations for a car, or they're trying to predict the weather. Those involve these huge systems of differential equations, much more complicated than anything you'll ever see in math class. But the weird thing is you can't solve them. So even though in calculus class they give you these differential equations that you can solve by like organizing stuff and integrating both sides, that doesn't work in the real world hardly ever. And there's some equations you can't actually solve. Like there's no mathy way to solve it. All you can do is approximate the answer. But of course, since we have supercomputers now, you can have a pretty awesome simulation or approximation if you know what you're doing. And that's kind of what a slope field is. So when they have you do a slope field and they give you an initial condition, like, start at this point. If we start at this point, we'll get a different function, obviously, than if we start at this point. So let's start at this point. And what they're saying is, hey, just kind of follow the flow, right? Just whatever things are flowing, just go that direction. And that's exactly what Euler's method actually is. Because if we were following, but this isn't very accurate. And I'm sure you had the same thought I do when I'm looking at these, like, I don't know, like that, or geesh, and then it gets steeper, I don't know, and then it does a really hard kick, but how big a kick is it? I don't know. And you kind of know, like if you got this point over here, you and I both know this is not a very accurate number. It could have been you could have messed up to the tune of this or this. Like the error bar on this, point is ridiculous. But what would have happened if the slope field was much closer together? What if they'd given you a slope field that was like ultra, like little tiny print? The more slopes they had given you, the better your guess would have been, right? You almost could have if they had given you a bunch more lines, you almost could have just connected the dots without having to guess what's going on between here and here. So that's what Euler's method is kind of all about. First of all, it's about, instead of just looking at arrows, we're going to actually calculate the slope at any given point. And then the smaller your step size, the more often you sort of look at that compass and try and see which direction you should go, the better your guess will be. So a smaller step size is equivalent of having a lot more vectors in your slope field to choose from. The smaller your step size, the closer it is connecting the dots. So what we're doing in Euler's, and we'll forget about the formula for a second, what we're doing in Euler's, we're saying, hey, let's start at a given point just like we did in the slope field example. Except instead of like eyeballing it and trying to see, gee, where does those vectors go? We're just going to plug it in. We're just going to take f prime, dy dx, also known as f prime. That just allows you to calculate the slope, right? So they literally just given you a formula to tell you the slope anywhere you want to be. So we're going to say, you know what? At x equals 0, I'm going to calculate the slope, and I'll just plug and chug that 0 through the slope equation. I'll get an actual slope. And then I'm going to go a certain distance, and that's the step size. You'll keep stepping the same amount. You don't have to. You could go 0.1, and then 0.7, and then 0.3. If you wanted to, there's no reason mathematically that you can't jump around and make small step, little step, small step, little step. But of course, mathematicians like to be consistent. So what we're actually going to do is take the same size step all the time. So let's say we're doing a step size of 1. So we're just going to, march along. So what we'll do is we'll start at 0, we'll calculate the slope at 0, and then we'll go that direction that it says to go until we get to x equals 1. And then we'll stop and we'll say, you know what? We've gone 1 already. Maybe the slope changed already. I'll tell you what, let's recalculate the slope, only this time we'll calculate f prime of 1. So we'll know the slope where we are now, not the slope back there. And we'll find out what that direction is. And let's say the slope we got is this. It's negative 0.5 or something. So we're like, okay. So for my next step, I'm going to go in a direction of negative 0.5. And my next step is 1 long, of course. So now I end up right here. Now that we're at this point, guess what we'll do? We'll plug back into f prime. We'll get the slope where we're at now. So we'll calculate f prime of 2. And that's going to be the direction we should go in now that we're at 2. It's like, oh, that slope was positive 7. Well, that would be crazy. Plus 2. So like we'll go this way until we get to 3. And what happens at 3? We once again say, you know what? Maybe we should change directions. So let's go back and plug in. We'll get f prime of 3. That's our new direction. And we'll go that way for a little while. So you see how we're just like, instead of just eyeballing the arrows, we're instead calculating the arrow exactly where we are. Wherever we are, we stop, we plug and chug through the equation, figure out which direction to go, and go that direction. Now what happens if you do a smaller step size? Well, gosh, instead of going 1, because this one had a step size of 1, that's our delta x or our h, some books refer to it as. So instead of going 1 before we check our directions, well, let's just go half. Let's go 0.5. Because you can see how this is not very smooth. And this is like a big direction change. Did that really go like this, or was it like this? Who knows? A lot was going on right there. So let's do smaller steps. We'll still start at the same point, but we'll check our direction more often, and maybe it would have done like this. It could have been a quite different curve if we had been doing smaller steps. But again, all it is like if you get directions from someone and you're like following a compass, trying to go on a hike and you're following a compass, the more often you check your compass, the better you're going to do, like the straighter line you'll go in. Or not the more straighter line, but the more accurate line. So all we're doing is we're checking our compass more and more often. And of course, if you're a computer, what would you do? You're like, well, crap, I can make a really nice spreadsheet. I can make my step size 0.001 in Excel. And since it's automated, I'll just whip out, if I wanted to go from 0 to 5, that would be 5,000 lines in a spreadsheet, but that's okay. And actually, when I took differential equations in college, I was in an engineering program at Stanford, and I didn't actually take the mathy version of differential equations. This is all we did. So we'd set up these long spreadsheets that would spend like 5,000 lines just approximating how to get from here to here to get as accurate as possible. Because the more often you check your compass, the more accurate you'll be. And that's what step size is. So that's why I always, in these problems in the book, they'll always say, oh, do this problem first with a step size of 0.1, then with 0.5. And actually, the two problems we're about to do, we're going to do that same thing. Well, for one of them anyway. We'll try 2 different step sizes and see how different our answers are once we mix up the step sizes. All right, so that's the theory in a nutshell. So where does this crazy formula come from? Well, we're gonna, each time we got to a point, so if I start here and then I go to here, at that point I have to recalculate things, right? So what's my next y value gonna be? If I go this way or if I go this way, whichever direction I'm going, my next y value is gonna be the previous y value. So if I wanna know whether I'm gonna be here or here, whatever, somewhere along this, next x, I'm going to figure out where am I now. So I'll take my current y value and then I'll add a little bit to it or take a little bit away. So I'm taking the current y value and then I'm adding this portion, which is like, if you remember y equals mx plus b, this is the mx portion. So the slope is f prime. So basically what we're saying is, hey, my next point, I'm going to go a delta x, and that's going to result in a rise or a fall of delta y. And what's the slope? F prime equals delta y over delta x, right? That's how you calculate slope, is delta y over delta x. So if you want to know what delta y is, if you want to solve this little equation for delta y, You just multiply both sides by delta x, and you get that delta y equals f prime times delta x. That's what this term is. It's delta x times f prime. So all this equation is saying is, hey, if you want your new y coordinate, take your old one, and then add delta x times the slope to figure out like what that little delta y was. This term is your delta y. If slope is negative, it'll end up being a negative delta y, and you'll have, your next y coordinate will be below the previous one. So delta y, if you get a negative value, all that means is, oh, it's not up here. The point was actually down here somewhere. But that's how we're going to work it. So let's just step through this one. Happens to be a word problem, which is, I think it makes a lot of sense to do a word problem because then you can actually sort of think about it a little bit. The next one we do will be your standard math class, like here's the derivative, here's whatever, here's your step size, plug it in. But in this one, let's say, hey, you're in a boat, you're rowing along, and it springs a leak. And the leak's getting worse. It's like some idiot, maybe there's a hole in the boat already, and some idiot plugged it with like chewing gum or water-soluble glue, like Elmer's glue, and as it starts leaking, the glue gets wet and the hole gets bigger. So it's like getting exponentially more leaky. And by the time you notice the leak at t equals 0, it's already leaked 40 liters. So they're telling us, you know what? The amount of water that's already come into the boat at time equals 0 is 40 liters. And then they're saying, hey, you figure it'll take you 4 minutes to get back to shore. Estimate how much water will come aboard in 4 minutes using increments of 2 minutes. So they gave us that delta x equals 2 minutes. And they're asking us for v of 4. So they want us to estimate v of 4. So how many steps are there? If you're starting at 0 and you want to get to 4 in increments of 2, that's just a couple of steps, right? You go v of 2 and then v of 4. And this one I'm not going to do a table. I'm just going to do it more intuitively and just plug and chug through the formula. In the next one, we'll actually use a table. So that's a pretty common method that teachers show you how to do it. The columns vary, but they're usually pretty similar. All right, so I already know that v0 is 40, right? That's just a given. So my next one that I'm going to guess is v2. So I want to approximate the volume after 2 minutes. And the way I do that is I take my previous y coordinate, which is the volume at 0 minutes, and I add delta x times f prime at the previous point I knew, which was 0. So I'm saying, hey, let's take the point we're at, and then let's take the slope at that point. Like what direction do we walk in at that point? And then we'll go with delta x, and let's find our delta y. So v0 we already know is 40. And then delta x is 2. And what's f prime is 0? Well, they gave us v prime, of course. I guess it's actually v prime, I should have said. Since in this particular problem, the function's called v, not f, but for volume, the amount of water that's come in. But what's v prime is 0? Well, gosh, well, let's take 0 and plug it in. So 1 plus 0 is 1, squared is 1, times 0.5 is 0.5, so 2 times 0.5. So 40 plus 2 times 0.5, which is 1, so 41. All right, so pretty exciting. So after one step, we've gone from 40 to 41. Our new y coordinate, our new amount of volume of water in the boat is 41. So now to get v4, so I go one more step, which is from 2 to 4. So to get v4, I take the previous volume that I knew, which is v2, and then I add delta x times v prime of that previous point that we just were at, and that v prime, that's v prime of 2. All right, so what's v of 2? Well, gosh, this is what happens. You just take the number you just got is the first term right here. So 41 just gets copied right down to there. You notice how 40 got copied to there, and now 41 is getting copied here. So that just always happens. That's part of the sort of the rhythm of these problems. The step size is still the same. So delta x is still 2. And then what's my v prime of 2? So we take 2 and plug it into this guy. 1 plus 2 is 3. Squared is 9, times 0.5 is 9 halves. And that 2 cancels that 2, so you get 41 plus 9 is 50. I'm going to circle it because that's the end. They wanted me to estimate v of 4, and sure enough, we've got estimated v of 4 is 50. All right, now we're going to repeat for an increment of 1 minute, and this is just to show you what we were talking about before, which is that the smaller your increments are, the better a job you'll do of following that function. So let's do it again, only with a new step size. So once again, we're going to start back at v0 equals, what they give us, 40. And then we're going to do the exact same process. We're just going to have to do it more times because we've got smaller steps. So v2, v3, and finally v4. So you can see this actually looks an awful lot like a table, doesn't it? All right, so v0 we already know is 40. V of 1 is where we're going to plug in. So v of 1 is going to be v of 0 plus delta x times v prime of the previous x, which is 0. All right, so v0 we already know is 40. Delta x now is 1. And then what's v prime of 0? I could just look back the previous time I worked it, but let's just plug and chug through again. 1 plus 0 is 1, squared is 1, times 0.5 is 0.5. So 40.5. And of course, what happens? I immediately take the number I just got and copy it down to the next line. Oops. After I write down the symbol version, which is, so v of 1 plus delta x times v prime of 1. Now we copy it down, so 40.5 plus 1 times, what is v prime of 1? 1 plus 1 is 2, so I'm looking back up here at the v prime equation. 1 plus 1 is 2, 2 squared is 4, times 0.5 is 2, so 2. So 40.5 plus 2 is 42.5. All right, so now my next one, I got v of 2. So this number is always 1 less than this number. Plus delta x times v prime of 2. And you can see how this pattern is developing. We got 0, 1, 2, 0, 1, 2, 1, 2, 3. It gets really repetitive. And then, of course, this number ends up getting used right here. So our delta x is 1, so I just could quit writing it down, but for some reason I keep doing it. So now what's v prime of 2? Well, go back to here. 1 plus 2 is 3. 3 squared is 9, times 0.5 is 9 halves, which is 4.5. Since we're doing decimals on this one, we might as well do the decimal version. 42.5 plus 4.5 is 47. All right, we're almost there. This is going to be our last row. So v of 4 is going to be v of 3 plus delta x times v prime of 3. So once again, I just take the 47 I got, copy that right down to the next row. Delta x is 1, and what is v prime of 3? Well, go back to the scoreboard here. 1 plus 3 is 4. 4 squared is 16, times 0.5 is 8. All right, so 47 plus 8 is 56. Nope, that's wrong, right? 55? What is it? Yeah, it's 55. Good job. Okay. All right, so pretty exciting stuff. So the second time, we did smaller step sizes, and we got an estimate of 55 instead of 50. So which one do you think is probably closer to right? The 55, right? The smaller step is pretty much always the right one. So hopefully this makes sense. You notice what we ended up with looks an awful lot like a table, and that's what we're going to see in the next problem. Is we'll do all this exact same stuff, but in table form. It ends up working out the same. So if you prefer the table, or your teacher prefers the table, go for it. I personally kind of like this, honestly, because the same patterns develop, and if you just kind of write in neat rows and neat columns, you'll end up sort of with a table-like effect anyways. So, to each your own, check out this table problem, and we'll see what you think. All right, this is the last one we'll do. It's basically the same problem. This one's more like what they'll actually give you, right? Like in lecture, this is what your teacher worked. It was a random function. It had no rhyme or reason. They didn't tell you what it would look like. They just said, hey, do this thing. I also want to demonstrate the table version of the situation. The one I just did, you could see how it looked an awful lot like a table. I mean, we just worked our way down. But in this one, we'll just actually use the actual table that a teacher would have you use. Now, I mix things up a little bit. You notice how I use, like, in the formula on the first slide of this video, we had, instead of xn and x minus 1s, we had xn plus 1 and then xn's. So either way, the point is, as you've seen in the previous problem we did, this is going to be one more than this. So this is the one we're trying to calculate. This is the x before the one we're trying to calculate. So that's just, you can kind of ignore those little numbers. That's just kind of what's going on. All right, so the way I'd set up a table like this, let's see, we're trying to get, so we're given that f2 equals 4. So our initial x value is 2, and then initial y value is 4. So in this first row, I'm never certain what to do in the first row because you basically need some empty spots. Because we're not actually calculating it, right? We know this, so we don't need to bother going through the whole equation. So we know that f equals 4 at 2. And then we want to use 0.1 increments to estimate f of 2.5. So basically, if it's a 0.1 increment, you just know you can fill this in right now. 2.1, 2.2, 2.3, 2.4, 2.5. And since we're working with a table, we could even fill in some other stuff ahead of time. For example, if we know that 4 is the y value at 2, that's the one we're going to put right here that's going to help us estimate, right? This is the same thing, this one here, and is just this. So I just made some columns that would make it easier to sort of plug and chug through the equation in this last cell by writing down the information ahead of time. Anyway, so this 4, you know that's just going to right here. And then I can't fill in this number because I don't know this number, right? This number is the one that's going to end up going right there. So I can't do that yet. What could I do ahead of time? Oh, what about f prime of x n minus 1? We could do that ahead of time because that's only based on the x values. And we know the x values already. All right, so what's this chamber going to contain? What's this cell? It's going to be f prime of x n minus 1, the previous one. So that means we're going to take this x, plug it into f prime, and put a number right here. So what's that going to be? If you take 2, plug it in this equation, you get 2 minus 3 is negative 1. And then we're going to take 2.1 and plug it in to get here. So what's f prime of 2.1? 2.1 minus 3 is negative 0.9. And I'll take this 2.2 to plug in here. So 2.2 minus 3 is negative 0.8. So hopefully you see where I'm getting at. I'm just taking x values and plugging them into my f prime equation that they gave me. They always give you f prime or dy dx or whatever, because otherwise you can't solve it. What happens when I plug in 2.3 to that equation? 2.3 minus 3 is negative 0.7. And I'm just doing this because I like to calculate everything I can ahead of time because that just eases the flow of plug and chug. And then on 2.5, to get this f prime, we got to plug in 2.4. So 2.4 minus 3 is negative 0.6. All right, so we're getting there. All right, so now we're just going to be plugging and chugging through that giant equation. So you'll notice right here I wrote out the full formula that we want to use. We've already got 2 of these numbers in the table. So if I want to calculate 2.1, so if I'm filling in this row, I'm just going to take, what they're saying is it equals the previous f, so that's 4, plus delta x times f prime of the previous x, which is 2, f prime of 2. So that's going to be 4 plus delta x in this case is 0.1. And f prime of the previous x I already calculated as negative 1. So that's 4 minus, all right, so now I just figured out that at 2.1, I think the y value is 3.9. So now what do? I take the 3.9 and immediately copy it down to here because that's the starting point of my next little increment. My next little walk I'm going to go on starts at 3.9. And then what's going to happen to it? Well, when I start at 3.9 and then I go delta x plus delta x times whatever direction I'm walking in. So delta x at this point is 0.1 still. And then of course I want f prime of 3, which is right here. So I'm just going to take that number, that's the f prime for this row. So negative 0.9. So that's 3.9 minus 0.09, because 0.1 times 0.9 is 0.09. So I get 3.81, which I immediately take down here and put right there. All right, so for my next little jaunt, I'm starting at 3.81, and then I'm going to go an increment of 0.1 at a slope of negative 0.8. So that's 3.81 minus 0.08 is 3.73. What do I do when I get 3.73? I immediately copy it down as my new starting value for y on this row. So now I got 3.73 plus my step size of 0.1 times this new slope, which is negative 0.7. So 3.73 minus 0.07 is 3.66. Once I get 3.66, I immediately go over here, copy it down there, and now that's my starting point for this step. And this is my last step, because once I'm done with this row, I will have calculated f of 2.5. So that's plus 0.1 times negative 0.6. So that's 3.66 minus 0.06, and we get 3.60. And I circle that one because that's the end of the road. That's my approximation. All right, so just for kicks, let's see what we would have gotten if we had done a one-step approximation. So in this one, we did pretty small steps, 0.1. So it took 5 steps to get from 2 to 2.5. But what if we tried to shoot it in just one step? That would be fun. So if we tried to shoot it in just one step with a step size of 0.5, let's see what happens. Well, gosh, in that case, our new value, f of 2.5, would equal the value we had before that, which is f of 2, plus delta x times f prime of 2. So I just took my previous y value and the slope at that previous y value, and then I multiplied it by the step there. So what was f of 2? Well, just like we started with, f2 is 4. That was given in the problem. Plus, and now this time we're doing a step size of 0.5, and what's our slope at 2? Negative 1. So that's 4 minus 0.5 is 3.5. So in this case, the function was decreasing, but our bad estimate was actually lower than our better estimate. The smaller your step size, the better the approximation is. That's just the way it goes. And it'll pretty much, I mean, you'd be hard pressed to find a problem where you have a worse approximation doing smaller steps. I'm sure there's one you could cook up, but it would be wacky. Anyways, point is, in this case, we actually underestimated by using the longer step. And maybe that's because the slope was negative this whole time, so it was decreasing, so wacky. Maybe it was kind of curving like this. So in the previous ones, when it was a sort of upside down parabola, we overestimated by doing larger steps. In this one, we seem to have underestimated, so I'm guessing the curvature was positive, but anyways. Point is, it's kind of tricky, but the smaller the step size is, the more accurate you'll be. And once you get in this table, or if you do it with the equations like we did in the previous problem, it becomes a step-by-step plug-and-chug kind of deal. So once you get yourself rolling. But I hope that now it's pretty clear that what's going on is we're just basically checking our compass, taking a step, checking our compass, figuring out which direction we should walk in now, go in that direction, calculating that new position, then saying, okay, what's our direction now? Go that direction for a minute. Okay, check our compass. What direction should we go now? Go this direction, calculate that new y coordinate, and you can just do this all day long. I don't know what, I guess this would be the Euler's approximation of a sine function or something. Anyways, good stuff. So hopefully I'll see you around. Euler's is fun. Not really, but at least it's plug and chug, which a lot of students appreciate, once you get the hang of the table.